In this lesson, we're going to look at measures of variation, and the big measure we're going to look at is called standard deviation. So our objectives here, that you can describe the data using measures of variation, range, variance, and standard deviation. Mainly standard deviation is the big key here. And that we're going to use technology to do this. And to understand standard deviation and its relationship to what's called the empirical rule. Okay, some terms to know. The range. The range is just the difference between the high and the low values. Not very useful because it's not a robust statistic, right? It's very, it'll change by the outliers, and the outlier themselves would be a high or a low value. Standard deviation, we will use either the letter S for a sample standard deviation, or the Greek letter lowercase sigma for the population standard deviation. And variance, which is occasionally used, particularly in theoretical work, is just the standard deviation squared, represented by S squared or sigma squared. Okay, so the formula looks, it may look somewhat intimidating. So here is the sample standard deviation formula. It's a square root of, and this little sigma right here, this just means sum. So we're going to add up, we're going to take the x value, whatever data point it is, subtract it from the mean, and then square it. Add up all of those, divide by n minus 1. N is the number of items in my data set, and then take the square root of all that. Okay? Population, very similar, except we're going to divide by n rather than n minus 1. We use a Greek letter mu to indicate this is the population mean. Okay? So by hand, we'll show you just one of these by hand. So below here are times in minutes it took for Domino's to deliver a pizza to our house. So 22 minutes, 30 minutes, 27 minutes, and 39 minutes. So find the standard deviation. The sample, we're going to pretend this is just the sample. This is not the entire, I didn't go out and look at every, count every time Domino's delivered pizza to someone's house. This is just my house. Sample the last 5 times. Or is that 4 times? 1, 2, 3, 4. 4 times. Okay, so step 1. That little x bar is right there. And our problem, x bar was 29.5. Okay? And I assume that you can find the mean. We had an earlier lesson on that. We just add those up, divide by 4. So remember the formula right here. Our formula is we have x minus x bar and then square it. So just to kind of keep track of everything, here are my x's. These are all my values, 22, 30, 27, 39. I subtracted from the mean, which was 29.5, so 22 minus 29.5 is a negative 7.5, etc. 30 minus 29.5 is 0.5. Do that, and then we square it. Okay, if we didn't square it and we added these up, we get 0. So we square it. And when we square it, just put it in the calculator. You've got to make sure when you put it in the calculator, you put the entire value squared. You got to use parens. And now doing this little sigma, the sum part, I just add those up. I get 153. So 153 is what goes right there in this numerator. The entire numerator is 153. You can see why this would not be fun to do if you had 100 data points. It would just take a while, right? So I put that 153 in for the numerator. N minus 1, well, n was 4, right? So 4 minus 1 was 3. Where'd I get the 4? I had 4 data points. I crunched that out. 153 divided by 3 is 51. The square root of 51 is about 7.14. That is a standard deviation. So what does that number mean? That tells us how much the data vary from the mean. And the more of these that we do, that number will start to make sense to you. And what's a big standard deviation, what's a small standard deviation, etc. We will be mostly using software on here. I don't think I'll have you do any of these by hand, maybe one at the most. But we'll be using our TI and some software to crunch this out. So step one, you press stat and you enter the list into L1. And you basically do the same thing we did when we computed the mean and median. Remember how to do that? Press stat, enter the data into L1, press stat again, and scroll over to calc and select one variable statistic. One variable stats, I guess I should say, with an S there. Step 3, when we press that, you may want to select the list L1. You don't have to. You can just press the one variable stat and press enter. Once you press enter, here is our sample standard deviation, about 7.14, the same thing I obtained when I did it by hand. So just so you can see me do that live if you need to, I'm going to clear this out, press stat, enter. I've got a list in there already, so I'm going to scroll up, press clear, enter, and now put the data in. 22, 30, 27, and 39. I press stat, scroll over to calc, and select this top one variable statistic. I could just press enter or get in the habit of telling me that the values are in L1 and press enter, and there it is, standard deviation. It also gave me the mean at 29.5. I could scroll down and look at the median as well. Okay, move that out of the way. Okay, another one, example 2. Suppose you want to determine which pizza restaurant delivers your pizza the fastest and most predictable time. So how much does it really vary? You order 5 pizzas from Papa John's and 5 from Domino's, and record the delivery times in minutes. Ooh, I'm actually getting kind of hungry now thinking about this. We're going to calculate the mean, standard deviation, and draw a conclusion. So if you want to, go ahead and pause the video here and bring your calculator up and see if you can go ahead and do this one on your own. Okay, welcome back. I'm going to press stat, edit. I'm going to clear that list out. I always clear rather than, you could go in with only 4 values and just press delete on the numbers themselves. I typically don't even tell people to do that because they'll mess up. They'll scroll up here and press delete, which you don't want to do. Okay, I'll put 55, 45, 5, 15, 40, and 20. So those are the times for Papa John's. So 1, 2, 3, 4, 5, 6. So I actually have, this should say 6 pizzas. I always check that out. I check to make sure I have at the very least I have the same number that I've got. And then quickly scan and make sure you typed them in right. We'll put L2, we'll put Domino's in for L2. 32, 28, 31, 29, 27, 33. Alright. Now we're going to go to stat, calc, just do one variable statistic. And I may be able to do 2 variable statistic here. Let's try that. I don't use that very often. And press enter. And it actually does give it to me. So I've got the mean. So L1 is the X bar. So the mean for Papa John's is 30. Standard deviation, this is a sample, so it's 19.4. I scroll on down, the Y is L2. So the Y is Domino's. Again, a mean of 30. Standard deviation of 2.4. Now normally I don't use the 2 variable statistic. I basically just go into stat calc 1 variable statistic. And let's do L1. Because oftentimes I want those other numbers that it didn't give me, the Q1s and medians and things like that. So again, I've got X bar is 30 for Papa John's, and as I recall, it was 30 for Domino's. The standard deviation for Papa John's is 19.4. So S is about 19.4. 0.49. And the standard deviation for Domino's, I don't remember what it was, but we'll go back, stat, calc, 1 variable statistic. But I gotta press L2, second 2. I get the X bar of 30 again, but the standard deviation is 2.37. Just round to 2 decimal places is fine in this case. Let's move this down. Okay, so I had that already up there. So what does this mean? I mean, look at the data. Look at what the standard deviation is telling us. The smaller standard deviation, this data for Domino's varies much less. It hovers much more tightly around that mean of 30 than Papa John's does. Papa John's is all over the place, right? So it's going to have a greater measure of variability, so a greater standard deviation. Oftentimes on standardized tests, you're asked the question, you'll be given 2 data sets like this, and it'll say which one has the greater standard deviation. And without even using a calculator, we ought to be able to see that Papa John's is going to have a greater standard deviation. It definitely varies much more than the Domino's. Okay, example 3. To order food at a McDonald's restaurant, one must choose from multiple lines. At Wendy's restaurant, one enters a single line. The following data on the next slide represent the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. For each sample, answer the following questions here. What was the mean wait time? So we're going to find the mean for both McDonald's and Wendy's. We want to draw a histogram for both of these. And then which restaurant's wait time appears more dispersed? Which one would you prefer to wait in and why? Okay. So let's come over here. So here's the wait time at Wendy's and wait time at McDonald's. So you can put this into the calculator or the software, and I think I've got some help for you here in a moment. You can watch me do that. It's the same way you do it when we did the mean with Minitab or StatCrunch. Let's look to see how we could do this in StatCrunch. So I'm going to press Stat and Summary Stats for the columns. We want the summary stats for both columns, so we'll select both Wendy's and McDonald's, and we'll most likely leave these blank most of the time in here. Make sure the summary stats that we want are in here. We'll just leave this as the default. You can see what else we can get. And click Calculate. And there we go. So now let's go ahead and do part B and do a histogram of the data. Graphics. Click on histogram. Again, we want histograms for both of these. Let's have a bin width of 0.5. When I didn't do this earlier, when I tested this out, it made one of them had a bin width of 1 and one of them 0.5, but I want both of these to have the same bin width, rather than having it automatically calculate. We don't need to overlay a density, but we are using multiple graphs, so just to make sure we kind of get the same, we have the same scale, let's use the same X and Y axis. Sometimes this really skews what we're looking at, so you just have to kind of experiment with it. This one will look pretty good, I think. And we'll avoid the title and labels for now. And we can look at these. If we did rows per page, if we wanted to look at these on top of each other, we could do it like that. Create graph. And it puts them on top of each other. I kind of like looking at them that way most of the time. We could change that and make it 1 row by 2 columns, and they're beside each other that way. They both kind of had their pluses and minuses, right? We can look at it that way fine, I think. So let's go ahead and move this down. So here are the histograms, and we'll talk about these in a moment. Okay, so now we have, I put both of these into a Word document so I could write on the screen a little bit easier. So the first question asked about what is the mean wait time. And so we can look here at the mean wait times. And they're about the same, right? About, if we ran to the nearest hundredth, it's 1.39. What do we are here in minutes? In minutes, 1.39 minutes. So identical wait times, pretty much. What do we notice about the standard deviation? Now the question actually asks which restaurant wait time appears more dispersed. So which one here appears more dispersed? We can look at the histogram here, and because I chose the same axes, it's a little bit easier to tell, I think. The McDonald's wait time appears more dispersed, right? It's we see that it's heavier all the way across. The Wendy's wait time, the largest ones right here, a lot of them cluster right in here. And sometimes it's kind of like reading tea leaves when you're looking at these histograms and we look at other plots. So we do have a numerical calculation we can look at, and that's the standard deviation, the measure of the variation. So we notice that McDonald's wait time is 1.26. The Wendy's standard deviation is 0.74. So we see here that McDonald's does have a larger standard deviation, so a more varied wait time. You could have also answered, so I would rather wait in the Wendy's line, that sort of style of a line. You could have answered McDonald's, I guess, if you wanted to. We just need to provide a good reason here. We look at the medians. You may say, well, the median wait time for McDonald's is much lower than the median wait time at Wendy's. So with statistics, there's not always a right answer when interpreting some of these. So just make sure that you give a rationale for why you choose what you choose. I would prefer to be in the Wendy's line because the wait times are more consistent. They're more closely aligned with the mean wait time of 1.38 minutes. Whereas McDonald's are all over the place. You could certainly answer McDonald's though, because you can look over here at the median and go, well, hey, the middle wait time is 0.86. So there are a couple different answers you could have given there. The empirical rule. So this is something you'll need to sort of memorize. We see this shape show up a lot in what we've been looking at. This is called the bell-shaped curve or the normal curve. So the normal curve, or sometimes called the bell-shaped curve, I'm sure you've heard of that. We can actually glean a lot of information just from the curve itself. This is a theoretical curve, right? Nothing ever turns out perfectly distributed this way. So some things we're going to learn on here is how we can figure out these values here. So one standard deviation from the mean. So here's the mean at x bar. X bar plus one standard deviation. We have 34% of the data to the right and 34% to the left. So 68% of the data are within one standard deviation of the mean from a normal distribution. 95% are within two standard deviations. And 99.7% are within three standard deviations. Okay, and then we can get these individual percentages here just by subtracting and dividing out. Okay, so have that curve in your head, or write it down, or hopefully you have these notes printed off. Okay, so we're going to work a problem here where we would use that curve. SAT math scores have a bell-shaped distribution with a mean of 518, standard deviation of 114. What percentage of SAT scores is between 404 and 632? I may have to go back to this. I don't have my notes printed out. But here is the curve. So when you're doing these, you will always draw out your curve. I've seen students do this without drawing a curve out. They are crazy. Always draw this out. So math, bell-shaped distribution with a mean of 518, standard deviation of 114. So that's how I write it out. I put the mean in the middle, and then I put the standard deviation right below it in parentheses. Okay, and so now we want to fill out the rest of these numbers here. And so if you can't add these in your head, I'll show you a quick way to do that. Just go 518 plus 114. We get 632. And then plus another 114. And we get 746. And we'll go about one more. Plus 114. And we get 860. And then do the same thing except go to the left of the mean. We'll do 518 minus 114. So 404. And then do another minus 114. 290. And then do one more. And you're probably already way ahead of me. Minus another 114. 176. Okay. So let's move this out of the way. And so here is our curve. Now what was our question? I forget. So between 404 and 632. 404 and 632. So what would the answer to that be? If we look back at that empirical curve here, 68% fall within this region right here, no matter what these values are. So what percentage? We would say 68%. And that's how we use that. What percentage of SAT scores is less than 404 or greater than 632? So here we're looking for less than 404. So we're looking from 404 and all this area right here, or greater than 632. Normally we would shade all that. You would draw separate curves. So there's a couple of different ways we can do that. We already know this right here is 68%, right? From here to here. What's the total percent underneath the curve? It's 100%, right? 100% is underneath the entire curve, so how do I get those little pieces right there? I just subtract 68% from 100%, and I get 32%. You could have gone back and used this curve here and added those up, and you'd get it. But think for a second. I think you'll get it. What percentage of SAT scores is greater than 746? So let's look here. We're looking for this little piece right here. So greater than 746. So we're looking for 2 standard deviations above the mean. We can go back over here. And what do we get here? So 2 standard deviations above the mean is 2.4 and 0.1, which is 2.5. So 2.5, and hopefully that makes sense here. We have 95% are here to here. So that means there's 5% left in the tails. So 5 divided by 2 is 2.5, because we got 2 tails. However you want to do it is fine with me. So 2.5%. So that would be really tricky if you didn't have that drawn out. So make sure you draw these out. Okay, example 5. Return to the body temperature problem. This is a great data set. I'm using it throughout. Compute the variance in sample standard deviation for the body temperature. And then B, use the empirical rule to determine the percent of people with body temperatures between 97.52 and 98.98. Determine the actual percentage of people in the study with body temperatures between those numbers. And then use the empirical rule to determine the percent of people with body temperature above 99.66, and then determine the actual percentage. So we're trying to see, the point of this exercise is for you to kind of get another handle on finding the of using the empirical rule, but also seeing how the empirical rule actually does do a pretty good job of getting close to the actual percent. Okay, so on the calculator, we could put all... Okay, to create this standard deviation on TI, go ahead and press the stat button and press enter. Put the data into L1. Assume you can do that by now. It's the same way we found the mean and median. We're going to go ahead and press stat again, select calc, and one variable statistic. Go ahead and press enter. We can go second L1 just to make sure we got an L1 and press enter. And there we go. There's our standard deviation. All this data back in, and hopefully you've saved that data set from an earlier lesson in the calculator, or on Minitab, or in StatCrunch, or even Excel, if you so choose. So here's our mean, standard deviation, and variance, right? Now, this was a sample, so we're going to use our sample standard deviation this time. with the S, it can get a little confusing there. Just think about the problem. This was a sample of body temperatures that we're looking at. So we're going to use the 0.733. Now if I'm going to find the variance of that, I just square that number. So let me go ahead and do that real quick. So let's say 0.733183158, and then square it. So our variance here would be, if I'm going to write this out, so the variance, or S squared, is 0.5376. We'll round to 4 decimal places. Standard deviation, 0.7332. I'll need that up there to do my addition subtraction, right? So let's say the mean here is 98.2. We'll just run to the nearest tenth. 98, let's make that look more like a 2. Okay. Now let's go ahead and fill this out. So 98.2, well, let's say 0.25, as I think on the problem I rounded to the nearest hundredth. Let's make sure. Yeah, it looks like I did the nearest hundredth, so 0.25. So 98.25 plus 0.7332. That's 98.98. 98.98 plus another one plus 0.7332. 99.72. And then we'll do one more. I'm not sure. I don't think ours goes out this far, but we'll do one more anyway. Plus 0.7332. And we get 100.45. And now let's subtract. 0.25 minus 0.7332. 97.52. Hopefully I'm not rounding wrong here. Minus 0.7332. 96.79. And one more, minus 0.7332. 96.05. Okay, let's move this down a little bit. Now I need to go back and look at what the question was. Okay, so we computed the variance and sample standard deviation. Using empirical rule to determine the percent of people with body temperatures between 97.52 and 98.98. Okay, so we're looking at this right here again, right? And what do we know about that percentage? That is 68%, approximately. Okay, determine the actual percentage of people in the study with body temperatures between 97.52 and 98.98. So I will let you do that, actually. You can count through these. These are not sorted, which is not nice, right? When you pull this into your program, I would sort it and then just quickly make a count and see how that compares to the 68%. Okay, determine the actual percentage of people in the study with body temperatures between 97.5. Oop, we just did that one. Empirical will determine the percent of people with body temperatures above 99.66. Let's go over here and look at 99.66. Did I mess up there? Let me see. So 98.25 plus 0.7332 plus 0.7332 So just a rounding issue here. We will call this one here 99.66. I know some of you won't like that, but in statistics, we're going to have a little give and take there. So when I created that problem originally, I maybe did not include 4 digits. Maybe I included 3 or only 2 when I was adding, and so that created a slight rounding error when we did that. So let's pretend this problem here said 99.72. Hopefully on your sheet it'll say that. 99.72. And so the percent of people above this right here, this is 2 standard deviations above the mean, is, we can go back and look at it, it's going to be 2.5%. We can go back here and look at our empirical rule. Whoop, here we go. And again, 2.4% plus 0.1% is 2.5%. That's where I'm getting this from. And again, you can go in and count and see how many people actually had temperatures above the 99.72 and see how that compares. Okay, so in StatCrunch, to find the standard deviation variance, we're going to go over here to Stat, Summary Stat, and we've got a column here we're trying to find statistics for. We will just double click that. No need to group or anything, and just click Next. Oh, just make sure that standard deviation is in there and variance. We're good. Click Calculate, and there we go. So we have a mean here, 98.25, standard deviation right here, 0.733. Now if we wanted to create a histogram of that, close out of that, just go to Graphics, Histogram, Temperatures, Next. We'll do a frequency histogram and take all the defaults. And there's our histogram. You know, pretty much a bell-shaped normal curve. If I were doing this for real, I may want to go in and change this from whether 1 degree to maybe 0.5 or 0.4 degrees, just so I can see what's going on inside here a little bit better. Options, Edit, go back, and then bin width, maybe 0.5 would be better. That looks a little better. I'm a little happier with that. It doesn't give me the values here, but I know that's 97, I know that's 98 right there. So this gives me a better sense of the shape of the distribution. Okay, and also we had a question about the empirical rule. I told you to do it yourself, but I'll go ahead and show you. When we were looking for, we're trying to compare, we wanted to find the values, we're going to compare the empirical rule to the actual number of values that fall between, the first one was 97.52 and 98.98. So let me just kind of write those down here so I'll remember them. So it was 97.52 and 98.98. And I think we found 68% of the values actually theoretically would fall within that if it were perfectly normal. Now we're going to use here, so if this data weren't already sorted, I can go to Data here and sort columns. And we would sort the temperatures, and they'd be sorted over here under another column called Sort Temp. Okay, so we want to know how many fall between 97.52 So right here, and I can just kind of hold down the Shift button. Well, I guess I can't on this one right here. So we just look here, we're at row 20, right? For right here, so there's our first value. Actually, no, 97.52 would be this one. What am I thinking? So 97.52. Here's 97.6, that's our first value. At 22, so remember that. And then scroll all the way down to, we're looking at 98.98. So there's 98. 98.98 right there to 111. Right, so we went from 22 to 111. Okay, to find that out, we went from 22 to 111, so we just subtract. Let me bring this in here. 111 minus 22 is 89, but we've got to add 1. And that's because we're actually counting the 22. So plus 1. And we get 90. So just to make sure that makes sense, pretend we went from 108 to 111, and we include those values. So that would be, what, 1, 2, 3, 4. So if we did 111 minus 108, what do we get? 3. And we got to add 1 more. So we have to add 1 there. So just kind of be careful with that. So we get 90. Now the question is, what percent of that? So we got to see how many values we had to begin with. We had 130. And so I'm just going to do 90 divided by 130. And I get 69.2%, which you got to admit is pretty close to our model, our theoretical model, at 68%. And we can do exactly the same thing with the other one. It was above 99.66, I believe. And we have 1, 2, 3, easy to count those after we sorted them. And so we do that, and we end up getting about 2.3%, a little bit less than our theoretical projection of 5%. And so the same technique can be used in Minitab and even the TI 83 or 84.